Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the topic we are discussing in the last lectures. So let me write the topic. Our topic is application of statistical method to let me adjust my pen to gases. I will write here continued. So it is in continuation with the previous lectures. Under this heading today, we will discuss counting of microstates for gases. So we are moving ahead in discussing the application of statistical method to gases. Today, we will discuss this idea under this heading, counting of microstates for gases. So we already know that in the application of statistical method, counting up of the number of microstates consistent with a given valid distribution is vital. And we already know, once we know or count the microstates consistent with the given valid distribution, and we know that all such microstates are equally probable, so it is essential prerequisite to find the number of microstates. Once we know that, we can find the most probable distribution, which best describes the thermal equilibrium situation of the gas. And we also know that in gases, the particles are indistinguishable, as we already discussed. So we cannot know which particles are in which states. We can only know which states are occupied. Therefore, the counting of microstates is to specify the occupation of each one particle state in the gas, right? Now, the distribution whose number of microstates is to be counted is the group distribution already discussed in the previous lectures. I told you in case of gases, the number of states is large, so we group the states. So the distribution is that grouped distribution, and corresponding to that, we have to find or count the number of microstates. So let me refresh your memory with our symbols, which we used in the previous lectures when we discussed the application of statistical method to distinguishable particles. So if Ni is a valid distribution, In case of gases, this is a group distribution already discussed. Then we have denoted in the previous lectures by the letter T. So T of Ni means what? It means the number of microstates corresponding to this distribution. So it is number of microstates corresponding corresponding to the distribution set of Ni, right? Now to get this, we have to first consider the contribution in this number of microstates from each group of states. Then we can product them to get the total number of microstates for the distribution. And we will see that the contribution in this number of microstates from each group of states has a different form for bosons and fermions. Because we know fermions have a restriction of exclusion principle. We have already discussed that, but bosons have no restriction of Pauli's exclusion principle. So let us first discuss the case of fermions. We know in case of fermions, the exclusion principle operates. Therefore, the one particle states can only have occupation numbers of 0 or 1. That, in other words, means these one particle states can be either singly occupied or empty. This implies that in the ith group, let me write it, therefore, in the ith group of states, the number of particles Ni cannot exceed the number of states Gi. Why so? Because of the exclusion principle. If we take an ith group of states, the number of particles in that group Ni cannot exceed the number of states. So the counting is now straightforward. How it is straightforward? It is simple. Let me change the color. The group of Gi states, what we do, the group of Gi states, we divide it into two subgroups. Divide it into two subgroups. So we divide the group of Gi states into two subgroups. First group is, we know first that Ni of the states are to contain one particle. So one group is subgroup is Ni of states, Ni of the states that contain one particle, that contain one particle. Other subgroup, that is the remaining Gi minus Ni, states are, they must be unoccupied. We have, I repeat, Gi states in the ith group. We divide it into two subgroups. One subgroup is Ni of the states that contain one particle per state, and the other subgroup of the states, which is Gi minus Ni, because total states in the group is Gi. So other subgroup is Gi minus Ni. They must be unoccupied because total number of particles in this group is Ni, right? Now, how can we divide, or I should say, the number of different ways the states can be so divided? It becomes simply the binomial theorem counting problem. That is simply, let me write, the number of different ways the states can be so divided is simply Gi factorial divided by Ni factorial times Gi minus Ni factorial. Gi factorial divided by Ni factorial times Gi minus Ni factorial. And this is the contribution to the number of microstates from the ith group. Therefore, what about the total number of microstates? The total number of microstates corresponding to an allowable distribution Ni is given by, we have to product all the contributions. Let me write it in different color. I will use red. So the number of microstates, I will write T subscript FD corresponding to the distribution Ni is the product over I of these factors, that is gi factorial over ni factorial times gi minus ni factorial. Let me encircle this. I told you about this is the contribution in the number of microstates corresponding to ith group. So the total number of microstates corresponding to an allowable distribution is the product over all groups I. So let me name this as equation first. Let me check it. TFD of distribution Ni is product over I gi factorial over Ni factorial times gi minus Ni factorial. Now the subscript Fd is the short for Fermi-Dirac. Since these two physicists, Fermi and Dirac, were responsible for the first discussion of the statistics of what we now call fermions. So this is the case of fermions. Let us talk about bosons. There's another color for bosons. Now, as you know, as we discussed in the previous lectures, bosons are friendly particles. There is no restriction of Pauli's exclusion principle, and the statistics for bosons is called Bose-Einstein or BE statistics, named after its inventors. So counting the boson microstates is a little more tricky than the fermions, since now any number of particles are allowed to occupy any one particle state. I will write directly, then I will give you the home assignment. You can check the contribution in the number of microstates corresponding to the ith group. Here is written this way: Ni plus Gi minus 1 factorial over Ni factorial times Gi minus 1 factorial. What is this? This is the contribution to the number of microstates from the ith group. That is, it is the expression corresponding to this factor, corresponding to this equation in case of this expression in case of Fermi-Dirac statistics. Ni minus Ni plus Gi minus 1 factorial over Ni factorial times Gi minus 1 factorial. So this is your home assignment. Do this at home. Right? Now this is the correct answer to the problem. That is the contribution to the number of microstates pertaining to ith group. But bear in mind that in statistical physics, we're always dealing with large numbers, gi of states. So this minus 1 addition in the numerator and denominator we neglect. So we write it we neglect -1. So we write it as Ni plus Gi factorial over Ni factorial times Gi factorial. Ni factorial, sorry, Ni plus Gi factorial over Ni factorial times Gi factorial when we neglect -1 because Gi is large. So the total number of microstates therefore the total number of microstates for an allowed distribution for an allowed distribution for a boson gas, that is for a gas whose particles are bosons, for a boson gas is we have to product these factors. I will use another color here. Let me use this one. So it is, we call it TBE, that is the B stands for Bose-Einstein statistics pertaining to the distribution Ni. It is the product over I of Ni plus Gi factorial over Ni factorial Gi factorial. Let me encircle it. Call it equation 2. TBE pertaining to the allowed distribution Ni is equal to product over I Ni plus Gi factorial over Ni factorial times Gi factorial, and we know the product ranges over all groups I, right? Then there is another important thing, that is which we have to discuss. That is the case of dilute gases. Dilute gases. Remember, for gases there are two and only two possibilities. The gaseous particles are either bosons, so they have symmetric wave function. There is no restriction of Pauli's exclusion principle. And another variety is fermions. Their wave function is antisymmetric. They are restricted by Pauli exclusion principle. However, it is profitable to consider a third form of statistics quite explicitly, namely that of a dilute gas. Now, what we mean by a dilute gas? This dilute gas here has a specific meaning. It is to suppose that for all groups I, for all groups I, The states are very sparsely occupied. That is, Ni is much, much less than Gi for all I. This is the meaning of dilute gas here. So when we say we are considering dilute gas, by that we mean for all groups I, Ni is much, much less than Gi. That means for all groups, the states are sparsely occupied. You can see, or we will discuss it later, that this holds for real gases in the limit of low density and high temperatures, and that it corresponds to a classical limit to either the Fermi-Dirac or the Bose-Einstein form of quantum statistics. Remember the expressions we wrote for TBE and TFD, that is quantum statistics. So when we give the condition of dilute gas to Fermi-Dirac distribution, Fermi-Dirac statistics or Bose-Einstein statistics, those expressions reduce to the same form. We will see that. Before seeing that, you need to understand in this dilute limit, we can readily see that both forms of statistics, we will see that, give almost the same answer for T of a valid distribution Ni. It is a result we should expect, since when Ni is much, much less than Gi, even for bosons, we would anticipate that almost all the states are unoccupied and just a few have a single occupation, right? Now we will see now that the expressions we wrote for Fermi-Dirac statistics, that is equation 1, and the Bose-Einstein statistics, that is equation 2, they approach the same form when the gas is dilute. So consider first the fermion case. So consider the fermion case. Now in fermion case, each factor in equation 1 can be written as, in equation 1 can be written as, let me write it, Gi times Gi minus 1 times Gi minus 2, so on, up to Gi minus Ni plus 1 divided by Ni factorial. Gi times Gi minus 1 times Gi minus 2 times Gi minus Ni plus 1 divided by Ni factorial, where both numerator and denominator have been divided by Gi minus Ni factorial. Let me write it, where both numerator and denominator have been divided by by gi minus ni factorial. So we take the Fermi-Dirac expression, equation 1. Now we have many factors in it. Then what we do, we modify or write the numerator differently and divide the numerator and denominator by gi minus ni factorial. When we do that, we get this. Gi times gi minus 1 times gi minus 2 up to gi minus ni plus 1 divided by ni factorial. Check it. Check this. Check it. That way. Right? So you see now when you write it this way, the numerator of this expression is the product of ni factors. Is the product of ni factors. That is one thing. All of these factors are almost equal to gi. They're actually a bit less than gi, but as you know, gi is large. You can approximate all these factors to gi, and the factors are ni. So this numerator simply becomes in this uh, this limit. When we talk of this dilute limit, that is ni is much less than gi, all factors become approximately equal to gi, and they are ni factors. I can write them as gi raised power ni. Therefore, TFD becomes product over I gi raised power ni by ni factorial. So this is the number of microstates corresponding to a valid distribution ni according to Fermi-Dirac statistics, but for a dilute gas in that limit when all the states are sparsely occupied. Let us move to now the second case, that is the Bose-Einstein statistics. Now in the boson case, let me write it in the boson case, equation 2 can be treated similarly, can be treated similarly in this dilute limit, in the dilute limit. So dividing the top and bottom by gi factorial in equation 2, dividing the top and bottom, that is numerator and denominator, by gi factorial, we obtain let me write we obtain for a typical factor, a typical contribution, or you can say term, we get this gi plus 1 times gi plus 2, so on up to gi plus ni over ni factorial. Gi plus 1 times gi plus 2 up to gi plus ni over ni factorial. What we have done, we have taken equation 2, that is this equation for Bose-Einstein statistics. We have divided the numerator and denominator by gi factorial. As I told you, in the dilute limit, we can write it this way. Again, you can see the numerator is the product of ni factors, each approximately equal to, they are across a bit larger than gi, but in the dilute limit, ni is very small compared to gi, so you can treat all the factors approximately equal to gi. Number of factors is ni. So for dilute boson gas, I can write TBE is approximately the product over I gi raised for ni divided by ni factorial. Right? So see, both the Bose-Einstein statistics and the Fermi-Dirac statistics reduce to the same thing in this dilute gas limit. Therefore, in the dilute limit, as I told you, as we discussed and proved, that TFD and TBE tend to the same value. Now, this classical limit is called the Maxwell-Boltzmann case. This classical limit is called the Maxwell-Boltzmann case, discussed by these famous scientists before quantum mechanics was conceived. And we write the answer to our third counting problem. Now we call it as TMB. MB stands for Maxwell-Boltzmann. Product over I, gi raised power ni divided by ni factorial. I name this equation 3. Right? So according in this case, Maxwell-Boltzmann case, that is the classical limit to Fermi-Dirac and Bose-Einstein statistics, the number of states, microstates corresponding to a valid distribution is given by equation 3. So I stop here. Before stopping, I would summarize today's lecture. So, in today's lecture, we continued with the application of statistical method to gases. So, today we discuss how we count the microstates for gases. First, we considered the case of fermions and wrote this expression. Then we talked about the bosons. I gave you here homework problem to prove this. Then we talked about the dilute gas limit, and we showed that in the dilute gas limit, both Fermi-Dirac and Bose-Einstein statistics reduce to the same result, which we call Maxwell-Boltzmann statistics. So this is all for today. Go through all the lectures and do all the home assignments I give you in the lectures. Don't forget to like, share, and subscribe my channel. Assalamu alaikum.